What really happened after the extinction of the dinosaurs? How did life recover from such a devastating catastrophe? 66 million years ago, a giant asteroid struck the Earth, ending the reign of the non-avian dinosaurs and upending the global ecosystem. But from the ashes, a new world was born. Dear traveler, welcome. Today we're setting off on another extraordinary journey through time to discover the secrets of a reborn Earth. From lush forests to arid deserts, from deep oceans to icy peaks, we'll explore how life reclaimed its rights and adapted to give rise to the landscapes and creatures we know today. But before you set off on your next adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thanks, and have a great trip! After a catastrophe such as the one that occurred at the end of the Cretaceous, it's hard to say which species perished during the crisis, whether they were those that perished before the crisis, dying of old age, disease, or drowning, or those that survived the crisis and still found themselves in the same fossiliferous groove. Fortunately, in recent years, technology has evolved and our knowledge of the subject has been refined. There are also some particularly rich sites that are a veritable open book on our history, a kind of trapdoor that allows us to visualize the world of the past. This is a gold mine for scientists who can draw on the information engraved in stone to retrace the course of history. They help to rule out certain hypotheses, but also to distinguish between species that disappeared before the crisis, during the crisis, or survived it. This kind of place, where history is literally engraved in the rock, can be found at Coral Bluffs, Colorado. A few post-dinosaur fossils had already been spotted in the area. Scientists are therefore continuing their investigations at the site, but this time with a twist in terms of the method and type of trace they are looking for. Rather than searching for bones, which may or may not be post-crisis without being absolutely certain, scientists like Tyler Lyson decided to study rock concretions. A concretion is the thickening by accumulation of matter, often in successive layers on a rock surface or from a point of water flow. This means that geological and climatic elements and even traces of events can be determined with greater precision. Unlike a fossil found in other conditions, here the elements collected are linked to other elements in the concretions, making them all the more meaningful and enriching in historical terms. This gives a broader perspective on a period and enables us to draw on other fields such as geology to gather much more precise data. For example, scientists can accurately date fossils collected frozen in volcanic ash thanks to the orientation of the minerals, which changes according to the periodic inversion of the Earth's magnetic poles. It's as if rocks could speak and tell us what happened. A historical and chronological comic strip, as they unfolded at the time, unfolds before the eyes of the researchers. Animal fossils, plant fossils, mineral fossils, and geology in general allow scientists to determine who lived at a given time, but also how they lived and what were the key episodes in their history. Tyler Lyson is an American paleontologist who is widely recognized in his field. His discoveries included a coda dinosaur fossil, a duck-billed dinosaur of the hadrosaur family, but he is also at the forefront of important research into the evolution of turtles and the evolution of mammals after the dinosaurs. Tyler Lyson and his colleagues chose to focus their post-dinosaur research on rock concretions rather than bones, and this choice paid off. In the rocky concretions of coral bluffs, the scientific group unearthed mammal skulls, teeth, reptile skeletons, fossilized spores. In all, more than 1,000 vertebrate fossils, as well as almost 6,000 leaves and no less than 37,000 pollen grains, bear witness to their presence on Earth during this pivotal period in history. Thanks to the discoveries made by scientists, we now know that mammals were able to rapidly develop and diversify. We also know why and how. Plants played a decisive role in their rise. Let's discover the vegetation of the time to better understand the close link between mammals and these plants of a new era. Here we are in the middle of the vegetation cover that could be found in the aftermath of the Cretaceous. You'll notice that many of the plants around us are ferns. These ferns come in all shapes and sizes, covering a wide area. They were the first to emerge from the torpor that reigned after the biological chaos our planet underwent. A few mammals survived this biological crisis and found refuge and food in this green carpet. It has to be said that they had assets that enabled them not only to cohabit with the dinosaurs in their day, but also to keep up with them. Small in size with fairly basic metabolic needs, endowed with good hearing, and above all the ability to live at night, these animals were able to brave the sky darkened by the debris and ash dust of the planetary volcanic winter. Before going any further with our investigations into this plant cover, let's take a moment to understand where we are, and above all, when we are. The Cretaceous put an end to the reign of the dinosaurs, or at least the non-avian dinosaurs, since birds are still around today. But it also put an end to the Mesozoic. After this fifth mass biological crisis, a new period and a new era began, that of the Cenozoic. Previously, we saw the Paleozoic, meaning ancient, then the Mesozoic, meaning middle. Now we come to the Cenozoic, which could be defined as recent. This period, which continues to this day, began in the aftermath of the dinosaurs some 66 million years ago. Cenozoic, meaning recent life or new life, comes from the Greek kainos, new, and zo, life. This gives you an idea of the new departure in biodiversity during this period. The Cenozoic is divided into two major systems. The first is called the Paleogene and includes the Paleocene, Eocene, and Oligocene. Next comes the Neogene, which comprises four periods: the Miocene, the Pliocene, and finally, the Quaternary Era, which includes the Pleistocene and the Holocene. Geographically speaking, things have changed and had a major impact on climate, and by extension, flora and fauna. Pangaea is no more, and continental drift continues. Gondwana land is increasingly fragmented, cracking on both sides. Australia drifted northwards, while Antarctica took its place at the South Pole. The detachment of Australia and Antarctica and the creation of the Drake Passage led to a significant cooling of our planet. As a result, the climate is noticeably colder in some places, while in others it is warmer and wetter. Towards the end of the Paleogene, during the Oligocene, sea currents also changed, particularly near South America and the Antarctic. Indeed, when these two continents were joined, warm currents bathed the sides of Antarctica. These currents provided a warm climate for a rich jungle to flourish. But when the Antarctic broke away, it offered a passageway to the colder marine currents. The Antarctic Circumpolar Current is born. It brings Antarctica's deep, cold waters to the surface. Little by little, 33 million years ago, it became a veritable continent of ice. To sum things up, at the beginning of the Cenozoic, some continents broke away, others gradually dried up, and new land masses appeared, notably in northern Africa and Europe, which were once archipelagos. During the Eocene, India and Eurasia collided, closing the Tethys Sea. Elsewhere on our planet, geological upheavals continue. The Atlantic Ocean, for example, has settled comfortably between Europe and North America. The subduction of the Pacific Plate beneath the Americas is causing the Sierra Nevada and the Andes to rise. These changes are not insignificant. Biodiversity is closely linked to geological and climatic factors. Continental migrations, ocean closures and openings, and other tectonic upheavals have consequences for climate. The planet is warming. It's getting warmer, but it's also getting wetter. If the milder temperatures of the Paleocene allow plants to develop and expand their territory, like our famous ferns we met earlier, the humid tropical climate of the Eocene is a real springboard for the development and diversification of vegetation. Interestingly, the diversification of these plants can be compared with that of mammals. To give an order of magnitude, there are around 31 species of mammal at the beginning of the Paleocene. These animals took advantage of their strengths to survive, but also of the ecological niches left vacant after the disappearance of the dinosaurs. These are not surviving species that simply escaped the global catastrophe, but new species. New leaf eaters that didn't exist before and are gradually taking over. By the end of the Eocene, there were almost 120 species of mammal, 4 times as many as just a few thousand years earlier. Even flying mammals such as bats were present. The ascent is therefore meteoric. The mainstay of this ascent is plants. As soon as they diversify, they open up new evolutionary opportunities, unexplored ecological niches. In the space of 700,000 years, a tiny period of time on the scale of life on Earth, flora grew exponentially and above all diversified. Flowering plants, seeds, nuts, legumes, and even the first vegetables provided a varied diet that enabled many species to specialize. Some mammal species even went from weighing less than 600 grams to over 50 kilograms or 110 pounds in the same period. When we speak of the Mesozoic, we mean the era of the dinosaurs. The Cenozoic era, on the other hand, could be seen as the era of mammals, as they managed to find their place on our planet during this period. However, it should not be assumed that mammals were the only species living on planet Earth during this pivotal period. Reptiles, as well as birds and giant birds in particular, were also major groups to populate the land during this same period. The Cenozoic is divided into three major systems: Paleogene, Neogene, and Quaternary. A few years ago, the Paleogene and Neogene were grouped together under the term Tertiary era, but in view of recent discoveries, this has fallen into disuse and remains less appropriate than the Paleogene and Neogene, which stand for Old Genus and New Genus respectively. Let's begin our journey in Paleogene territory. The era stretches from 66 million years ago to around 23 million years ago. This era is itself divided into sub-periods, so that we can better grasp the different evolutions over the 40 million years it defines. We speak of the Paleocene, then the Eocene, and finally the Oligocene. Welcome to the very first period of the Paleogene, the Paleocene. The vegetation of this period is quite similar to that of a tropical rainforest. Made up of giant trees 40 meters or 88 feet tall, this forest is home to sassafras, walnut, and even tropical chestnut and sequoia trees, which are colonizing more and more territory. Beneath these giants are smaller trees and shrubs such as ficus, palms, and of course our famous tree ferns. The ground was covered with ferns, such as this asplenium, providing shelter for many species, but also allowing many insects to proliferate. In the marshy areas bordering the lake, the vegetation is a little different, with typhas, reeds, and water lilies, for example. There are also a few tall trees, such as cypress and nyssa. In other, more arid zones, the first cacti make their first appearance. Plant cover diversifies according to climatic conditions and geographical zones. Little by little, new species take the place of plants less able to survive and develop. But, like any self-respecting ecosystem, climate, flora, and fauna are closely linked. So it's only natural that fauna should adapt, specialize, and diversify as plants evolve. Of course, many mammals were present in the Paleogene. In fact, they were the dominant group in the Cenozoic, despite the large number of birds and insects. In fact, the Cenozoic is often referred to as the Golden Age of mammals or the Golden Age of therians. The term mammal is well known, but therian is less so. It defines and groups together the three main types of mammal found on our planet. We speak of eutherians for placental mammals, metherians for marsupials, and prototherians for monotremes. The monotremes, like the platypus, are the most unusual mammals in the therian group. It's a mammal, but strangely enough, it lays eggs. Let's take a look at some placental mammals first. They come in all shapes and sizes, as you'll see. There are small quadrupeds like this Propaliotherium, ancestor of the horse, barely 60 centimeters or 24 inches at the withers, as well as large mammals like this one, which weighs in at around 2 tons and is almost 4 meters or 13 feet long. It's an Uintatherium. If Uintatherium has generous measurements to say the least, this animal, of the Dinocerata group, also known as Uintatheres, was originally much more modest in its lineage. Early species measured just 175 kilos or 390 pounds. That's a lot, but not much compared with the 4,000 kilos or 8,800 pounds of muscle it now displaces. At that time, you could also have met a Phenacotus. It's probably one of the oldest ungulates known today, about the same size as our present-day tapirs. But we'll come back to the ungulate group a little later. First, let's look at the mammal group in the broadest sense. There are 3 types of mammals: placentals, marsupials, and monotremes. From the Paleocene onwards, the rise of mammals has been quite meteoric. 2 lineages quickly emerge within the group: the creodonts, which generally led to carnivores, and the condylarthras, which led to herbivores and omnivores. Phenacotus, which we've just seen, is one of the condylarthras. Its teeth are adapted to chewing plants. If you take a closer look at its feet, you'll see that it has 5 toes on both front and hind legs, each fitted with a small hoof. During the same period, but not sharing the same environment, you could have come face to face with a coryphodon if you had ventured into the marshes of Europe, China, or even North America. It feeds on aquatic plants. The coryphodon is very impressive, yet it too is a herbivore. Its musculature and jaw are impressive. 500 kilos or 1,100 pounds for 2.5 meters or 8 feet in length. Are such prey safe with such an imposing body mass? No, not necessarily. It all depends on the predator and its capabilities. A carnivore 14 meters or 46 feet long, 80 centimeters or 31 inches wide, weighing up to 1.5 tons, with a 40 centimeter or 16-inch cranium, and razor-sharp teeth could take on such prey. Titanoboa ceratogenensis meets all these requirements, unfortunately for our coryphodon. Living near rivers in present-day Colombia, it is the most imposing snake the world has ever known, feeding on giant freshwater turtles and even nearby crocodiles. That's not to say that the only real predators worthy of the name were reptiles. In the Paleocene, there were many other dangers faced by terrestrial herbivores. While many mammals are still vegetivores, granivores, or insectivores, there are some pretty impressive carnivores in their group too. Arctocyon is a fine example of the transition between these 2 regimes. The size of a large dog, it weighed up to 50 kilograms or around 110 pounds. Equipped with robust molars for crushing and powerful masticatory muscles, it is able to tear off leaves and chew efficiently. Yet it has impressive tusks visible on the mouth side. Are they canines? Nothing is less certain, but scientists believe that this rather unspecialized animal probably had an omnivorous diet, and it is assumed that it was in the process of switching from a carnivorous to a vegetarian diet. Other mammals with a similar silhouette had a meat-only diet. These are the Mesonicians. They are nicknamed hoofed wolves. Their nickname is very telling. They have the silhouette of a wolf but are equipped with 5 fingers, then as they evolve with 4 fingers ending in small hooves. They were very good runners and walked on their fingers. Native to Asia, they quickly established themselves as formidable predators. Disacus, a genus descended from the Mesozoicians, gradually spread to Europe and even North America. Another genus, Ankylodon, ventured as far as New Mexico and was the size of a bear. Disacus was closer to the size of a jackal. Like the other genera of the Mesozoic group, his dentition became increasingly differentiated and efficient. It has modified molars for shearing, slender lower molars for shredding, and sharp teeth for slicing. Andrewsarchus mongoliensis can also be found on the plains, weighing 400 kilos or 880 pounds, and measuring around 4 meters or 13 feet long, and nearly 2 meters or 7 feet at the withers. It was a very impressive predator. Later, Megistotherium osteophlastus, a member of the group that appeared in the Miocene, was even more charismatic and dangerous, weighing up to 800 kilos or 1,800 pounds depending on the source. Mammals adopt different diets, morphologies, and environments. Their diversity is great. As early as the beginning of the Eocene, the second period of the Paleogene, we can even see flying mammals. The bat in question is Violacea sigae. Taking advantage of caves for shelter, it fed on insects. What's really interesting about this bat is its ability to maneuver in flight. While far from being able to perform the feats of some of today's birds or even bats, it was nonetheless very gifted for a group of recently flying mammals. Paleogene birds, on the other hand, were not always gods of the skies. On the contrary, some enjoyed the land far more than the air. Mammals may have diversified greatly and are quite numerous in the continent, but they are far from being the only tenants of our planet. Giant birds, some of them also known as terrible birds or terror birds, have largely earned their place on Earth. Just a few million years ago, pterosaurs dominated the skies. The Cretaceous-Paleogene biological crisis having passed, things have changed quite a bit since then. With flying reptiles gone, an ecological niche remained. It was the dinosaur avians who would evolve into birds that would fill the gap. Many of them took to the skies, but a few preferred life on the ground. Birds underwent an incredible radiation during the Cenozoic. Several groups and families underwent a meteoric rise. First of all, there are the gastergnathids, which we'll talk about in greater detail later on, which are large land birds. Then there are the Plotopteridae, which are large seabirds. Then there are what we might define as primitive penguins, but also pelagornithids, bronthornithids, and phorusrhacids. It's the latter that will be nicknamed the terror birds. While some birds are herbivores, phorusrhacids are not. They are even reputed to be super predators. Unable to fly, they measure up to 3 meters or 10 feet in height, and can weigh up to 200 kilos or 440 pounds. These terror birds live in South America. One of the largest is Titanus wieleri, but it arrived on Earth a little later in the Neogene. These birds established themselves slowly but surely during the first part of the Cenozoic, but it was during the second part that they were at their most fearsome. Before reigning terror in South America, these flightless super carnivores were found elsewhere in the world. The oldest known forest racid, Lavocatavus, is thought to have been found in Africa. Scientists are still investigating the reasons for this possible migration. Eleutheronus, also relatively large, could reach 1.5 meters or 5 feet in height, and was found in Europe, notably in France and Switzerland. Let's take a look at two other very characteristic birds of the period, which don't belong to the Forest Racidae group, but to the Gasternythidae. The first is a giant bird called Gastornis, while the second is Diatryma. Gastornis is very tall, around 2 meters or 7 feet. It doesn't fly, but it runs. Its diet has long been the subject of debate. It has to be said that given its silhouette, scientists were keen to count it among the predators, and yet its morphology left a few doubts. In the end, it was Delphine Angst and Eric Buffetade, two specialists in paleontology, who succeeded in demonstrating through their various studies that it was indeed a plant eater. As for the second, Diatryma, you're probably thinking that they're eerily close in physical terms. Well, you're absolutely right. To tell you the truth, they're even the same animal. In fact, back when prehistoric animals were first discovered in the 1800s and 1900s, on more than one occasion, two different scientists described and named similar dinosaurs. Sometimes they were closely related dinosaurs, but of different species. For others, like Gastornis and Diatryma, they were indeed the same animal species. Over the years, the name Gastornis has stuck. Let's leave the birds for a moment and get back to some reptiles. Apart from our famous Titanoboa, others also crisscrossed the world's continents and waters during the Paleocene. Many reptiles disappeared after the Cretaceous, including flying and marine reptiles. But a few groups managed to establish themselves more permanently. These include crocodiles, snakes, lizards, and turtles. Here, in this Paleogene region close to bodies of water, we can admire animals, such as this Diplocynodon, part of the Alligatoridae family, or this Eoconstrictor snake. At the end of the Paleocene, temperatures soared. We're talking an extra 8 degrees Celsius, or 14 degrees Fahrenheit. This is enormous. Many species will not survive this turnaround. This fracture will lead to a so-called minor extinction. Although not on the scale of the end of the Cretaceous, for example, it nevertheless marked a new turning point for flora and fauna. This episode marks the end of the Paleocene and the beginning of the Eocene. Temperatures fell again for most of the rest of the Cenozoic, even leading to an ice age at the end of the period. During the Paleogene, the seas continued to recede, and new land appears again and again. When we look at the planisphere, we see that the position and shape of the continents increasingly resemble what we know today. India comes into contact with the Eurasian plain, and the Tethys Ocean is partly closed. This marks the beginning of the Himalayas, one of our highest and most beautiful mountain ranges. Further north, Greenland also broke away from Europe. Other animals appeared during the Eocene and Oligocene. Predatory mammals like Andrewsarchus mongoliensis. It is one of the largest carnivores of the Eocene plains. It can grow to 4 meters or 13 feet and weigh around 400 kilograms or 880 pounds. Other bats have also joined the family, such as the Archaeonycteris lasmicedon, undoubtedly a carnivore. And then there are groups that were already present, but which managed to conquer an ever-expanding territory at the expense of other species, such as rodents. In the living world, it's all a question of adaptation and survival. When a species fails to adapt, it becomes extinct. This is what undoubtedly happened to the multituberculates and what served the cause of the first rodents to become established. These small mammals, like those of the Cryptobatar genus, hopped about like gerbils. They were omnivorous and had teeth quite similar to rodents. Scientists believe that the disappearance of the multituberculates is linked to their competition with rodents. Both groups occupied the same ecological niche. As rodents are equipped with hypsodont and chisel-like incisors, they seem to have fared better than multituberculates. Without this key evolution, multituberculates would have disappeared from the landscape. Apart from rodents, we're also seeing more and more lagomorphs, i.e. rabbits and hares. But the great revolution of the Eocene was undoubtedly the appearance of the primate lineage. They were quite similar to our present-day lemurs. The canopy has become much richer and more diverse over the last few thousand years. There are more and more deciduous trees, but also flowering trees, and above all, fruit trees. And yes, let's not forget that angiosperms, i.e. flowering plants, have developed considerably and expanded their territory. All this food is a godsend for these primates, who make their home high up in the trees. The first mammals capable of climbing trees had to come down to feed. But there are plenty of predators down there. To offset the danger, some mammals developed finer motor skills in the trees, but also found food in them to increase their chances of survival. Their vision becomes sharper, their legs become hands, an opposable thumb appears, they gain balance. In short, they colonize the trees and offer themselves an impregnable kingdom in the heights, thanks to new physical abilities. As far as we know, Purgatorius is probably one of the oldest representatives of our primate ancestors. This small animal lives in North America. The one hanging over our heads is a Darwinius macillae. It belongs to the Notharctidae family and comes to us from Europe, in Germany. Notice the opposable thumb. As you can see, their morphology is quite similar to that of today's lemurs. Slender, and agile. Eocene primates found in Asia, Africa, and North America already display most of the group's typical features: prehensile feet, binocular vision, and nails instead of claws. Most Eocene primates, especially those from Eurasia and North America, belong to several groups, the most important being the Notharctidae and Omomidae. Many primates will disappear after the Eocene, at least most of the taxa native to North America and Europe. The surviving taxa will be of Asian and African origin. Some Eocene mammals are particularly important for the rest of our history. Paucacetus, for example, is probably a distant ancestor of whales. Yes, despite what you might think, the ancestor of this enormous aquatic animal actually lived on land, not in the ocean. Hyracotherium is also an emblematic animal of the Eocene, whose genealogy led to animals we still know well today. Hyracotherium is thought to be one of the most distant ancestors of the horse. Propaliotherium and Paleotherium followed. Arsinoitherium would be related to our present-day elephants, although I agree that it looks a lot like rhinoceros. The distant relative of rhinoceroses would be this one, Megacerops, a brontotheron. In the same group, the brontotheroids also include Embolotherium, with its nasal horn and 2.5-meter withers. Both belong to the parasidactyls, i.e. ungulates with an odd number of digits, such as horses, rhinoceroses, and tapirs. Conversely, those with an even number of digits include bovids, cervids, giraffids, camelids, and, incredible as it may seem, cetaceans. Megacerops, on the other hand, has an odd number of toes and is therefore a parasidactyl, like horses and tapirs. Speaking of tapirs, here's a member of the Tapiridae, Lophiodontidae, whose typical representative is Lophiodon, a close relative of today's tapirs. During the Oligocene, grasses became increasingly abundant, and a few small meadows appeared on the horizon. This was an environment that had not previously existed on Earth. Ungulates, or hoofed mammals, were the first to colonize this new ecological niche. Several species of Rhinocerotidae, Equidae, and Chalicotheriidae are found in Europe, Asia, and even North America. In Europe, these are mainly Chalicotheriidae, such as Chalicotherium. It measures around 2.5 meters or 8 feet in length and weighs no less than 350 kilograms or 770 pounds. In North America, it's the equids that are evolving quite markedly. New forms are appearing, such as Mesohippus, which is becoming increasingly similar to today's horse. We can see that not only its silhouette has evolved, but also its skeleton. The premolars are molariform. This makes it easier to crush even tough leaves. In Asia, rhinocerotids are particularly abundant. Paraceratherium, for example, is one of the species that took up residence in Asia during the Oligocene. These large herbivores are beginning to reach some pretty impressive sizes, this one reaching 5 meters or 16 feet in height, and no less than 15 tons. Not all of them have such dimensions, however, and there are many smaller rhinocerotids developing in the region. The development of grasslands and the expansion of flowering plants also served another animal group, insects. By the Cretaceous, numerous groups had already emerged. Beetles, such as beetles and ladybugs, could already be observed at this time. There were also Diptera, which we often like a little less because of their sting, as in the case of the mosquito. The last to arrive were the Hymenoptera, including bees and wasps. This little world is about to welcome newcomers, the Lepidoptera, which includes butterflies. During the Oligocene, we meet up with our Paucacetus again. Well, not quite. We're going to meet one of its descendants. And as you can see, this one has already returned to the water. We're talking about Ambulocetus. His name means the walking whale. This gives you an idea of some of its present and future characteristics. Ambulocetus, like Himalayacetus and Indocetus, is able to take advantage of both terrestrial and aquatic environments, as was once the case for certain amphibians. This evolutionary perspective may have its origins in the emergence of new land masses and the gradual retreat of the sea in these Eurasian regions. A little further out to sea, we may also come across a cotylochore. The cotylochore is a type of dolphin that is physically very similar to our modern-day dolphins. In fact, according to scientists, cotylochores, like them, were probably capable of echolocation. But these marine mammals aren't the only ones in the water. There are large predators to be wary of. In the waters of the Paleogene, over a period of almost 25 million years, chondrichthyans, cartilaginous fish like the shark, dominated the world's waters. With the great diversity of actinopterygians, i.e. ray-finned fish, these great predators were spoilt for choice when it came to their menu. Food galore, hunters inevitably thrive, and sharks find themselves at the very top of the food chain. But that doesn't stop the few marine mammals that thrive beneath the waves. Descendants of Ambulocetus and other primitive whale congeners, for example, continue to evolve. Towards the end of the Oligocene, Basilosaurus appeared. He belongs to the Archaeocete group. Far from the image we have of a marine mammal, it was once considered a reptile. Scientists named it Basilosaurus saurus, referring to its reptilian condition. It has to be said that its silhouette is almost identical to that of a snake. Yet many years after its discovery in 1834, study of its skeleton showed not only multi-rooted teeth and a single jawbone, characteristic of mammals. What really confirms the diagnosis, however, are its forelimbs, which truly characterize it as a marine mammal on a par with whales. In fact, it is a descendant of Pakicetus and Ambulocetus. This 20-meter or 65-foot-long cetacean is a much-feared predator in the area. It has sharp, deadly teeth. In the marine world, there are much smaller forms of life. Particularly those belonging to the Foraminifera family are also developing, completing the food chain. Foraminifera include Nummulidae and Alveolinidae. Now it's time to leave the Paleogene and see what awaits us after, the Neogene. As we have just seen, the Paleocene was marked by many changes, both geographically and biologically. The end of the Paleocene marked the beginning of a new era for terrestrial flora and fauna. The Neogene begins on the Miocene. A number of geological changes continued. The face of the Earth gradually changed, even though this new geographical facet began several million years ago. The planet continued to cool, and the Antarctic continent became covered in ice. At the end of the Pliocene, pack ice even appeared at the North Pole. Then, during the Neogene, land routes began to take shape, inexorably impacting biodiversity. These routes brought South America into contact with North America through the Isthmus of Panama, Eurasia with Africa, the closing of the Tethys Ocean, which later became the Mediterranean Sea, and the appearance of the Strait of Gibraltar. These new contacts led to migrations, but also to competition, Yet another minor biological crisis was already on the horizon. At the end of the Neogene, some species become extinct, unable to adapt to new territories or to compete, while others diversify and expand their territories. Marsupials and placentals will be the big winners in this new adaptation. These changes, combined with the isolation of certain continents, apart from Europe and Asia, which remain united, led to the development of environments, fauna and flora specific to each continent. In South America, predators are limited to animals belonging to the marsupial or giant bird groups. Primates thought to have originated in Africa are also present. In North America, the evolution of equids continues apace. From the first horse, Hyracotherium, to the only surviving genus Equus, height at the withers increases progressively. Another evolutionary characteristic of equids is their feet. At first, only 3 of the 4 toes were preserved. Then a single toe became the hoof. At first, they eat soft food, such as buds or young leaves. Then their teeth evolved to better crush grasses and rougher leaves. Let's go back 23 million years to the very beginning of the Neogene to understand why this period of history was so enriching for biodiversity, both on land and at sea. Still in the Cenozoic era, after having traversed the Paleogene, we now continue our journey into a new era, the Neogene. It began 23 million years ago and ended 2.5 million years ago. Like the Paleogene before it, this system is also subdivided into different periods to better understand the 21 million years it defines. The Miocene, the first period of the Neogene, corresponds to the major part of this period, spanning the first 18 million years. It is divided into 6 stages. The following 3 million years correspond to the Pliocene, with 2 stages. Many other surprising and impressive animals await us during the Neogene. Before meeting them, let's take a look at their environment and the characteristics in which they evolved. Continents broke away from each other. New lands emerged and temperatures dropped throughout the period. Depending on the geographical zone, warmer and wetter environments appear, while others are colder. Geographically speaking, with less than 23 million years separating us from our present era, the position of the continent seems very close to the usual continental configuration we are all familiar with. If we're a little more observant, we can see that there are still a few small points that are far from settled. Greenland, for example, is not yet covered by its Neogene ice mantle, nor are the continents of South America and North America yet connected. After this brief geological and climatic overview, let's take a look at how flora and fauna evolved during the Neogene. After taking a dip in the ocean, here's the landscape you might have discovered during the Miocene, the first period of the Neogene. Although some species differ, you'll no doubt recognize the large families that live here around you. There are corals and sponges, algae, mollusks, arthropods, and lots of fish. As we saw during the Paleogene, ray-finned fish diversified greatly, providing an important ecological niche for many predators. Since the beginning of the Cenozoic, marine reptiles have no longer been the main beneficiaries, but chondrichthyans, cartilaginous fish, and in particular primitive sharks. They were already present in the ocean 300 million years earlier, as early as the Devonian for the oldest and the Permian for the so-called modern sharks, i.e., well before the dinosaurs. However, they were not in a position of strength and faced stiff competition, first with large arthropods such as eurypterids, then with Mesozoic marine reptiles, veritable sea monsters. During the Cenozoic, however, competition diminished, if not to say became virtually non-existent. They can evolve at will, and it's not the most impressive of them all, having inspired cinema's greatest sea terror, who will say otherwise. Is it worth introducing the monstrous megalodon? The Otodus megalodon shark is a member of the Otodontidae family. This impressive and intriguing family emerged after the Cretaceous crisis. It is therefore very recent, yet no less evolved and specialized. Megalodon live in shallow marine areas and warm waters. Other species, notably pinnipedomorphs such as this, Enaliarctos, are also making their grand entrance into the marine fauna. It could be the origin of the pinniped genus. It had a short tail, developed muscular limbs, and webbed feet for swimming. It was already well adapted to the aquatic environment, with vibration-sensitive whiskers, an inner ear capable of hearing underwater, and large eyes. However, this carnivore probably had to consume its meal on the surface, as its dentition, notably its sharp carnivorous teeth, did not allow it to do so in the water, so it went to the beach to enjoy the fruits of its hunt. Apart from the megalodon, these animals could come across other predators just as frightening as they were impressive. But they weren't out of the woods yet. Another large predator sailed here and there in search of prey to sink its teeth into. Leviathan melvillei is a sperm whale measuring around 15 meters or 50 feet in length, with a skull alone measuring 3 meters or 10 feet in length. Apart from its impressive length, you can see that its skull is heavily armed with a battery of teeth over 30 centimeters or 12 inches long, enough to make any prey that crosses its path shudder. Unlike today's sperm whales, which gobble up giant squid, the Leviathan devoured whales. During the Paleogene era, we mentioned another family, the cetaceans. By the time we left, this family was slowly but surely evolving. So what happened to them afterwards? To give you a little clue, scientists often refer to the cetacean era when they talk about the Miocene. As you can imagine, this was an extremely positive time for this group. Like the mammals before them, the cetacean order underwent such a rapid growth in species that two lineages were soon established. On the one hand, the Odontocetes, the toothed cetaceans, and on the other, Mystocetes, the baleen whales. The Odontocetes, or toothed whales, include dolphins, sperm whales, and orcas, which feed on fish, birds, and even a few mollusks. Mystocetes, with their filtered baleen plates, have a more restricted menu, generally limited to krill. The first Mystocetes, however, are more likely to have teeth than baleen plates, even if a lineage differentiation is already apparent. This is the case of Lanocetidae, Etiocetidae, and even Gangicetus, which date from the Oligocene. During the Miocene, Ebalenoptera could be observed, but it was in Piscobalena that the baleen plates were most clearly visible, as well as in Titanocetus. Now it's time to go back up to the surface to see how vegetation and fauna have continued to evolve. The Paleocene was also a pivotal period in the history of mammals. In a short space of time, they diversified and specialized, growing from a few grams to several hundred kilos. Some even went from being vegetarians to omnivores or carnivores. Initially, it was plants, among other things, that provided the springboard for such evolutionary radiation. Although their presence on the planet is still very important at this precise time, they are not alone. In addition to birds, they include numerous reptiles and a host of insects of all kinds. This new diversity in the world of plants and insects further encouraged the diversification of certain existing Paleogene groups, notably the herbivorous, granivorous, and frugivorous mammals of the heights, with a great period of evolutionary radiation in monkeys and bats. On land, too, mammals still have the monopoly. The biggest predators, apart from the terror birds of South America, are mostly mammals. Some of them can be quite surprising. The warthogs we know are generally more prey than predator. However, in the Miocene, it wouldn't have been a good idea to come across Entelodonte. With its imposing size, it could rival a bull in terms of mass and power. The largest of its kind, Entelodon magnus, could reach 2 meters or 7 feet at the withers, and was probably close to a ton of muscle. But its most impressive feature was its jaw. Like all mammals, its dentition is differentiated, so it has an armada of teeth in its mouth, enabling it to take on any prey in its hunting territory. It is tall on its feet and reputed to be a good runner. Scientists are unsure whether he was a carnivorous hunter, a scavenger, or a bit of both. In view of his build, power, and sharp teeth, we're tempted to think of him as an outstanding predator and the perfect hunter. However, some scientists are more inclined towards the opportunistic scavenger hypothesis. It's true that some of its teeth are perfectly shaped for crushing bones, making it the ideal scavenger. In any case, it remains an impressive predator. Just a few meters away lives the hyaenodon, which isn't very friendly either, to be honest. As for its diet, this time the scientists are positive. It's a carnivore, and a very good predator at that. Weighing up to 500 kilograms or 1,100 pounds, it is muscular, with powerful legs and 5 toes, armed with sharp claws. The long, narrow jaws were powerful and used for biting, neck-breaking, crushing, and crushing. With its 8 razor-sharp teeth, it rarely lost a fight with its prey. Other, lesser predators were just as agile and powerful in Europe and Asia. Cenozoic, for example, is a member of the Barbarophilidae family, weighing around 80 kilos or 180 pounds, with relatively short but powerful and muscular legs. Homotherium was a member of the saber-toothed feline family, made famous in prehistoric films and cartoons. Saber-toothed felines are known as Machaerodontinae, weighing up to 250 kilograms or 550 pounds and reaching 1.8 meters or 6 feet at the withers. These felines were quite powerful and impressive. The incisors and lower canines formed a powerful piercing device. Once the prey was caught in the predator's powerful jaws, there was no chance of escape. It also has long, slender legs, and it seems a very large nasal opening. This means it had a fast and efficient oxygen supply, and its legs were formidable when running. Elsewhere on the globe, predators were of a very different kind. In South America, marsupials and terror birds still have a monopoly on the territory. Among carnivorous marsupials, boar hyena comes to mind. With its long, powerful neck and jaw with sharp, jagged teeth, it was an impressive hunter. Its name echoes the hyena, as the front of its body, notably the head and long neck, are reminiscent of this opportunistic African predator. Australohyena, also a member of the Sparassodonta group, had a short snout, strong canines and molars for crushing. It was one of the largest predators in its environment, weighing up to 70 kilos or 155 pounds. It must have been able to break bones just like hyenas. Lycopsis longirostrus can also be mentioned in the same genus. Among giant birds, we can turn to Phorusrhacos to learn more about this group. He is considered one of the largest predatory birds ever to have existed. He belongs to the group known as terror birds, which also includes Titanus and Kelenkin. Phorusrhacos measures around 2.5 meters or 8 feet in height and can weigh up to 150 kilograms or 330 pounds. The most striking feature is its beak. It's huge and above all, hooked. To help him in his hunt, he also had a pair of claws on his wings and long legs that enabled him to run, according to scientific estimates, at up to 65 kilometers per hour, or 40 miles per hour. Kelenkin was even bigger, reaching a height of 3 meters or 10 feet. His head alone was 7 centimeters or 3 inches long. He had the same physical prowess as his fellow, Phorusrhacos, namely the speed and weapons to take on prey such as rodents, reptiles, and even small mammals. As we have already seen, with the end of the Paleogene and the beginning of the Neogene, flora and fauna became increasingly differentiated according to region and location. Climate, but also the isolation of certain continents, plays a part in this specialization and these different radiations. Traveling around lakes and forests during the Miocene, here are some of the animals you might have come face to face with. Some are calm and peaceful, others fierce predators. Several members of the rhinoceratid family lived in the Bosnia-Herzegovina region, including Brachypotherium brachypus, Lartetotherium sanseniense, Placiacarotherium balcanicum, and Hispanotherium. A little koala can be seen high in the forest in Australia. Towards the end of the Miocene, as we shall see, some land masses dried up. Eucalyptus forests, on the other hand, expanded. This is undoubtedly what led one of the genera to specialize its diet with these trees in particular. Still in Australia, what could be likened to a muskrat also lived. This was Acultidata, a strict carnivore unless it was omnivorous. A few fossilized remains do not allow us to define its diet with any certainty. Another forest animal, Pliopithecus. Pliopithecus is a monkey, a type of primate physically quite similar to the gibbons. Unlike gibbons, however, it had a very short tail. It is found in Asia, but also extensively in Europe. According to some studies on fossils found, our Pliopithecus may have been able to swing from tree to tree thanks to its long arms, rather than relying solely on the dexterity of its hands and opposable thumbs. When an animal uses this tree-to-tree swinging technique, it is said to be able to branch out. This is a major turning point for primates as they become increasingly agile at heights and can thus protect themselves from terror birds and other ferocious predators below. Speaking of canopies and tree climbing prowess, another animal, this time from South America, lived in the river plains close to the forests. We're talking about the giant sloth. In view of its size and weight, it was probably not, as today's sloths are, capable of living in trees. Several species of giant sloth lived in South America during the Miocene. Megalonyx is one of them. It had powerful claws for clinging to trees and, above all, pulling food towards itself. Megatherium was over 6 meters or 20 feet long and probably weighed almost 3 tons. The advantage of his claws, but above all of his height, was the food he could reach. Very few vegetarians could reach such a height, so he could occupy an ecological niche without worrying too much about competition. A little less tall, but just as impressive, is Eremitherium laurelardi. It measured 2 meters or 7 feet at the withers, but when it stood on its hind legs in search of food, it displayed 5 meters or 7 feet of robust muscle and bone structure. Still among the predators, but a little more generous in size this time, we can also observe in North America, Europe, and even Asia, Machairodus, a saber-toothed feline, Ichtherium, which belongs to the hyenas, and Amphictyon. Amphictyon is a subtle cross between a bear and a dog. Probably omnivorous, it had powerful paws and a thick neck like a bear, but a broad tail and wolf-like teeth. It could reach 600 kilograms or 1,300 feet, making it a predator high up on the food chain. In Eurasia, it was able to prey on species such as Dicroceras, a small cervid measuring 70 centimeters or 28 inches at the withers. It is the oldest known antelorid cervid. On the plains of Africa, certain mammals began to grow in size, especially the genus Proboscideans. Dinotherium is one of them. It is considered to be the largest land mammal ever to have walked the earth. According to sources and descriptions, Dinotherium could have measured around 3.7 meters or 12 feet in height, and weighed between 10 and 14 tons for the largest males. One of the main differences between Dinotherium and our modern elephants is its trunk, which is shorter, and its tusks, which are not attached to the maxillae, as is the case with elephants today, but to the mandible, i.e. the lower jaw. In Europe and North Africa, Archaeobelodon was a genus of proboscideans smaller than our elephants. Even so, it weighed between 2.5 and 3.5 tons. Closest to the water is a hexaprotodon. This genus groups together a large number of extinct species of hippopotamus. The main common feature that gave the genus its name is the jaw. These animals have 3 pairs of fairly pronounced incisors. Not to be confused with the rhinoceratid species we encountered earlier, which could also share the same environment, notably swampy forests and somewhat drier open plains. In the fresh waters, it was not uncommon to see an Ischirorhynchus. This freshwater dolphin belongs to the Platanestidae family, the river dolphins. Our little tour of the different environments of the Miocene is coming to an end. Why subdivide the Neogene into two parts, given that one of them was only 3 million years old? Even though it's relatively short, it's still very important. To begin with, we need to look at the Earth's temperature and dryness. The climate became colder and colder, and forests gradually gave way to savannas and grasslands. This process had already begun during the Miocene, but became much more pronounced during the Pliocene. This drastic change in the landscape had a significant impact on the fauna. The drying up of the land is very violent. The Tethys Ocean, for example, disappeared completely, replaced by a white desert of salt. The sea loses up to 1 meter per year, with all the direct and indirect consequences this entails. This episode is known as the Messinian salinity crisis. In addition to these climatic and geological upheavals, there's the evolution of a particular group, and above all, the emergence of a new genus during the Pliocene that is of great importance to mankind. Who are we talking about? If I answer Tomai, does that give you any idea? Around 7 million years ago, a primate close to the origin of the human lineage was discovered. Measuring 1 meter or 3 feet in height, it was bipedal and belonged to the hominid family. It shares many of the characteristics of the hominins, i.e. the subtribe comprising the hominids and the genus Homo. If we study dentition carefully, we can see that tooth enamel thickness is between that of the pangenus, i.e. chimpanzees, and that of Australopithecus. Another important fact in the evolution of this new lineage is bipedalism. According to its skeleton, in the presence of the foramen magnum, the spinal column was upright, implying possible locomotion on the 2 hind legs. Evolution towards the Australopithecine, Kenyanthropus, and then towards the Homo genus is underway. Humanity is in the process of being born, here in Chad. Tomai took his first steps on 2 legs here, on the outskirts of Toros, Manala, in the Jorab Desert. 7 million years ago, the landscape was very different from the one you see today in this part of Africa. A forest had grown up around the edge of the lake. In this forest, you could find tall trees, shrubs, and leguminous plants. Nearby, a savanna landscape could also be seen. Proboscideans, ungulates such as giraffids or equids, and bovids enjoyed the area, when saber-toothed felines such as Machairodus or hyenids were not around. To understand the appearance of Tomai, we need to go back in time. 16 million years ago in the Miocene, the Ponginae, the Asian lineage of orangutans, separated from the Homininae, the Euro-African lineage of gorillas, chimpanzees, and humans. Less than 10 million years later, Tomai upset the established order of the Homininae. The latter diverged into 2 new lineages, the Paninae, or chimpanzee lineage, and the Homininae, or human lineage. Sahelanthropus chidensis led the lineage to Orrerin taganensis, a hominin aged 5.9 million years, then a little later to Ardipithecus cadaba, aged 5.8 to 5.5 million years. The lineage continued to evolve over the millennia. Around 4.2 million years ago, Australopithecines made their appearance, with Australopithecus anamensis, the oldest known of the genus. Then, 3.2 million years ago, in present-day Ethiopia, Lucy entered the human story. This Australopithecus afarensis turned the scientific world upside down and shook all the beliefs we had previously held about this lineage. Based on in-depth analysis of the fossil remains, it would appear that Lucy was 25 years old. The fossil is quite complete, with around 40% of the bones recovered. This provides a sufficiently precise picture of the genus to which she belongs. The discovery was made by a project involving some 30 Ethiopian, American, and French researchers, co-directed by paleoanthropologist Donald Johansen. He was accompanied by geologist Maurice Taib, artist and paleontologist Claude Guillemot, paleontologist Yves Coppens, and student Tom Gray. A few years later, just 4 kilometers away, drowned in the Awash River, the skeleton of a 3-year-old child named Salam, meaning peace, was also unearthed. These Australopithecines lived in present-day Africa 3.2 million years ago at the end of the Pliocene. Lucy evolved in this savanna environment, able to live both on the ground and in the trees. She was also able to move into the rainforest so necessary for feeding. Grasses, succulents, insects, and perhaps even a few small animals completed her daily menu. It is possible that one of these Australopithecus species was the origin of the Homo genus, which appeared in Africa between 3 and 2 million years ago. Studies and research are continuing on this subject. Our journey ends on this African landscape and the new hope of the name Lucy. The rest is just the beginning of a new page for mankind and the story of a new journey. Seen from the sky in a million years' time, the Earth won't change that much. Sure, the continents will move, but no more than 45 to 60 kilometers or 30 miles from their current locations. The sun will continue to shine, rising every 24 hours, and the moon will orbit the Earth in about a month. But some things will change quite fundamentally. In many parts of the world, irreversible geological processes are transforming the landscape. The vulnerable contours of ocean coasts will change particularly markedly. An active submarine volcano off the southeast coast of the largest of the Hawaiian Islands has already risen above 3,000 meters or 10,000 feet from the ocean floor and is growing every year. In a million years, a new island will rise from the ocean waves, already named Lohi. At the same time, the extinct volcanic islands to the northwest, including Maui, Oahu, and Kauai, will shrink under the influence of wind and ocean waves respectively. With regard to waves, those studying rocks for future changes conclude that the most active factor in changing the Earth's geography will be the advance and retreat of the ocean. A change in the rate of rift volcanism will take a very, very long time to affect this geography, depending on the amount of lava more or less solidified on the ocean floor. Sea level can fall significantly, during lulls in volcanic activity, when the rocks at the bottom cool and settle. Scientists believe this is what caused the sharp drop in sea level just before the Mesozoic extinction. The presence or absence of large inland seas such as the Mediterranean, as well as the reunion and breakup of continents, led to major changes in the size of coastal shelf areas. To imagine the world a few 100 million years from now, we need to look to the past for clues to understanding the future. Global tectonic processes will continue to play an important role in changing the face of the planet. Today, continents are separated from one another. Vast oceans separate America, Eurasia, Africa, Australia, and Antarctica. But these immense expanses of land are in constant motion, and their speed is around 2 to 5 centimeters or 2 inches per year, i.e., around 1,500 kilometers or 930 miles in 60 million years. We can establish fairly precise vectors of this movement for each continent by studying the age of the basalts on the ocean floor. Basalt near mid-ocean ridges is quite young, no more than a few million years old. By contrast, the age of basalt near continental margins and subduction zones can reach over 200 million years. It's easy to take into account all these age data on the composition of the ocean floor to rewind the tape of global tectonics over time and to get an idea of the geographical mobility of the terrestrial continents over the last 200 million years. Based on this information, it is also possible to project the movement of continental plates 100 million years in advance. Given the current trajectories of this movement across the planet, it appears that all continents are heading for the next collision. In 250 million years, most of the Earth's landmass will once again become a giant supercontinent. Nevertheless, the exact structure of the future supercontinent remains the subject of scientific controversy. It is possible to take into account the current movements of the continents and predict their trajectory over the next 10 to 20 million years. The Atlantic Ocean will expand by several hundred kilometers or miles, while the Pacific Ocean will shrink by around the same distance. Australia will move north towards South Asia, and Antarctica will move slightly away from the South Pole towards South Asia. Africa will move slowly northwards across the Mediterranean Sea. In a few tens of millions of years, Africa will collide with southern Europe, closing the Mediterranean Sea and erecting a Himalayan-sized mountain range at the site of the collision. So the map of the world in 20 million years' time will look a little familiar. When modeling a map of the world 100 million years from now, most researchers identify common geographic features. For example, agreeing that the Atlantic Ocean will exceed the size of the Pacific Ocean and become the largest water basin on Earth. According to the extraversion theory, the Atlantic Ocean will continue to open up, and the Americas will eventually collide with Asia, Australia, and Antarctica. In the final stages of this supercontinent assembly, North America will close the Pacific Ocean to the east and collide with Japan, and South America will wind clockwise from the southeast, joining the equatorial part of Antarctica. All these parts are astonishingly combined with each other. Thus, the new supercontinent will be a single continent, stretching from east to west along the equator. The extraversion model mainly maintains that the large convection cells in the mantle located beneath the tectonic plates, will remain unchanged in their current form. In contrast, the alternative approach, known as introversion, takes the opposite stance, referring to past cycles of closure and opening of the Atlantic Ocean. Today, both supercontinent theories, extraversion and introversion, remain popular. Whatever the outcome of this discussion, everyone agrees that while in 250 million years the Earth's geography will change significantly, it will still reflect the past. According to some simulations, in around 200 million years' time, average temperatures on Earth should fall slightly below 12 degrees Celsius or 53 degrees Fahrenheit. At the same time, global sea levels will fall by around 200 meters or 650 feet. In this configuration, conditions for the development of complex life will remain quite favorable at low and mid-latitudes. Only after around 400 million years will average surface temperatures fall to around 10 degrees Celsius or 50 degrees Fahrenheit, and ocean levels drop by more than 500 meters or 1,640 feet from their current position. In this situation, all continents from north to south, even at moderate latitudes, will be covered by glaciers, and mountainous regions at equatorial latitudes will also be frozen. However, this cold snap will not be permanent. After a further 200 to 300 million years or so, an equilibrium should be established between the decrease in temperature due to the bacterial elimination of nitrogen from the atmosphere and the increase in the sun's luminosity. The temporary assembly of continents around the equator will mitigate the impact of ice ages and moderate changes in sea level. Where continents collide, mountain ranges will rise, climate and vegetation will change, and oxygen and carbon dioxide levels in the atmosphere will fluctuate. These changes will be repeated throughout Earth's history. A gamma-ray burst, or huge supernova, occurs less than 6,500 light-years from Earth, within 500 to 600 million years. Gamma-ray bursts are enigmatic phenomena that appear to be the most intense and energetic explosions in the universe, and astronomers assume that they are linked to extremely powerful supernovae. Fortunately, we have yet to observe a gamma-ray burst close enough to us to fully understand what is happening. So far, gamma-ray bursts have only been detected in other galaxies. But if such an event were to occur close to home on a cosmological scale, as it will in around 500 million years' time, less than 6,500 light-years from Earth, it could lead to a mass extinction. A gamma-ray burst directed in our direction, lasting just 10 seconds, could destroy at least half of the Earth's ozone layer. Large-scale ozone depletion could have devastating consequences on food chains, leading to the death of many species. A gamma-ray burst would annihilate life forms on the Earth's surface and in the upper layers of the ocean, which currently supply significant quantities of oxygen to our atmosphere. It turns out that gamma rays also decompose the oxygen and nitrogen present in the atmosphere. These gases would be transformed into nitrogen dioxide, better known as smog. This would envelop the sun over heavily polluted areas. If this smog were to cover the entire Earth, it would block out sunlight and trigger a global ice age. Due to tidal forces, the Moon has moved more than 20,000 kilometers or 12,000 miles away from the Earth. Even in the most favorable cases, the lunar disk can no longer completely cover that of the Sun. In 600 million years' time, all eclipses will be annular. The fate of the Earth is intimately linked to that of the Sun, which, like other stars, cannot shine forever. 50 million years after the Sun's formation, our star became a main sequence star. Since then, its luminosity has increased in an almost linear fashion, rising by around 1% every 110 million years. Within 600 million years, our Sun will undergo a gradual transformation, resulting in a progressive increase in both brightness and heat. This increase in the Sun's luminosity will have a significant impact on our planet, resulting in more solar radiation reaching the Earth. This increase will have an impact on the silicate minerals present on the planet, leading to increased weathering of these minerals. This, in turn, will affect the carbonate-silicate cycle, which is a geochemical process involving the interaction between carbonate and silicate. Increased weathering of surface rocks traps carbon dioxide in the soil in the form of carbonate. As water evaporates from the Earth's surface, rocks harden, leading to a slowdown in plate tectonics, which eventually comes to a halt when the oceans completely evaporate. With less volcanism to recycle carbon into the Earth's atmosphere, carbon dioxide levels begin to fall. For hundreds of millions of years now, the Earth has been experiencing a period of intense cold, with an average surface temperature of around 10 degrees Celsius or 50 degrees Fahrenheit. But now, the Sun's increasing brightness is triggering a rise in the Earth's temperature, generating a series of problems. The first signs of trouble will appear within 600 million years, but it's only when the average temperature reaches 47 degrees Celsius or 117 degrees Fahrenheit when solar luminosity is 10% higher than at present in 1.1 billion years' time that the situation will become critical. From that point onwards, the Earth will begin to lose water progressively, resulting in a modification of its atmosphere and becoming a humid greenhouse due to the massive evaporation of surface water. At this point, the amount of water in the stratosphere should increase. These water molecules will be broken down by the Sun's ultraviolet radiation via the process of photodissociation. As a result, hydrogen will escape from the atmosphere. The main result should be the disappearance of the oceans in around 1.1 billion years. This water vapor, raised in the stratosphere, will undergo chemical decomposition, separating into oxygen and hydrogen. This is when major changes will take place. Higher temperatures will cause the oceans to absorb more carbon dioxide, a gas essential to plant life. This absorption will reduce the amount of carbon dioxide in the atmosphere, causing an imbalance in the plant life cycle. It is estimated that the planet will be able to support highly organized life for another 600 million years from now, as current forecasts indicate that after this period, the Sun's increasing brightness will have a significant impact on the biosphere. The emerging scenario is therefore worrying, as not only will the Earth progressively lose its precious water, but also gas is vital for plant development. Together, these elements threaten the delicate balance of our ecosystem. The high temperatures projected for the future would cause the oceans to absorb more carbon dioxide, which would disrupt the biological processes essential to plant life, accelerating the problems associated with water loss and the degradation of our atmosphere. We will be approaching the Earth's carbon dioxide compensation limit, a critical point at which the balance between carbon dioxide and oxygen becomes unsustainable for photosynthesis. In around 600 million years' time, carbon dioxide levels will be lower than those needed to maintain the C3 carbon fixation by photosynthesis used by trees. Some plants, using C4 carbon fixation, can survive carbon dioxide concentrations as low as 10 ppm. Currently, 99% of plants use C3 photosynthesis. Their ability to convert sunlight into energy is gradually declining, leading to a general decline in plant biomass. If atmospheric CO2 levels fall, the survival of embryophytic plants becomes difficult, as they require a minimum concentration of around 10 ppm atmospheric CO2. It is highly probable that the evolution of living organisms will enable a certain number of organisms to adapt to these conditions by using a more efficient photosynthetic carbon acquisition mechanism. When levels fall below this value, complex plants begin to die, leading to a reduction in oxygen production. This decrease, combined with continued consumption by biota and oxidation of kerogen, which is organic carbon in sedimentary rocks, leads to a gradual decline in the atmospheric oxygen until it reaches zero within a few million years. Researchers estimate that plants that use the C3 photosynthesis process to fix atmospheric carbon dioxide should disappear in 600 million years, and C4 plants in 840 million years at the latest, due to the loss of carbon dioxide from the atmosphere. This massive disappearance of plants would have devastating consequences for all living beings as we know them today. Plants are at the very base of the food chain, providing food and energy for herbivores. Their decline means fewer food resources for herbivores, which in turn suffer adverse consequences. Their populations begin to decline, upsetting the balance of ecosystems. Without plants to produce oxygen through photosynthesis, animals would face a disastrous situation. Large endothermic animals, such as mammals and birds, would probably be the first to disappear, due to their higher oxygen requirements, compared to smaller endothermic and ectothermic animals. As atmospheric oxygen levels fall and temperatures rise, placental mammals will become particularly vulnerable. Not only do they have higher oxygen requirements than non-placental mammals, but embryonic development is also highly sensitive to excessive heat. Large herbivorous mammals would suffer from diminishing food resources as plant availability declines. Small mammals would be slightly less affected due to their lower oxygen requirements and surface-to-volume ratio, which facilitates heat dissipation. Placental mammals experience higher body temperatures than marsupials and monotremes, making them potentially more sensitive to rising temperatures. Birds may be better adapted to survival than larger mammals, as their generally smaller size means they need less oxygen. What's more, migratory birds in particular would be better equipped than animals of a similar size, thanks to their ability to travel long distances in search of cooler refuges. Nevertheless, the number of such refuges would decrease as temperatures continue to rise. These refuges would also be likely to be found at higher altitudes, where less land surface would be available, limiting population size as species migrate to higher altitudes. Ectothermic vertebrates such as fish, amphibians, and reptiles could survive longer than endothermic animals in this scenario, thanks to their better heat tolerance and generally lower oxygen requirements. However, reduced water availability would make some amphibian species more vulnerable in such an environment. Fish species would also be at risk, although rapid evaporation from the oceans would not occur at this stage. Marine species may have a better survival capacity than freshwater species due to the greater volume of ocean water compared with freshwater. For ectotherms, ambient temperature influences their metabolic rate. An increase in ambient temperature would lead to an increase in metabolic rate, and therefore a greater need for food. As a result, surviving species could be exposed to starvation. Reptile species whose sex determination depends on temperatures would be more sensitive to rising temperatures. Invertebrates could be the last animals on Earth before all animal species disappear. Some insects, such as beetles, can survive temperatures of up to 56 degrees Celsius, or 133 degrees Fahrenheit. In general, terrestrial life would initially be more vulnerable than marine life, due to the regulating effects of water temperature. However, the loss of terrestrial vegetation would lead to a reduction in nutrients reaching the oceans. Isolated communities in marine ecosystems, such as animal populations living near volcanic vents, would probably survive longer. Depending on the half-life of oxygen in the atmosphere, animal life could persist for up to 100 million years after the disappearance of plants. Some cyanobacteria and phytoplankton could survive without plants, as they are able to tolerate carbon dioxide levels as low as 1 part per million. They could persist until the atmosphere becomes too depleted of carbon dioxide to allow any form of photosynthesis. In one study, researchers claimed that a specific form of animal life could persist even after most plant life on Earth had disappeared. They used fossil evidence from the Burgess Shale in British Columbia, Canada, to study the climate of the Cambrian explosion, and used it to predict the future climate when global temperatures would rise due to a warming sun and decreasing oxygen levels, leading to the ultimate extinction of animal life. Initially, they expected some insects, lizards, birds, and small mammals to persist, as well as marine life. However, without a continuous supply of oxygen from plant life, they estimated that animals would probably die of asphyxiation. Even if enough oxygen were to remain in the atmosphere, thanks to the persistence of some form of photosynthesis, steadily rising global temperatures would lead to a progressive loss of biodiversity. As temperatures continue to rise, the last animals will be forced to move to the polar regions, or even underground. They would mainly be active during polar night periods, and would go into aestivation during polar day periods due to the intense heat. Much of the Earth's surface would become an arid desert, and life would concentrate mainly in the oceans. However, due to a decrease in the input of organic matter from the land, and a reduction in dissolved oxygen, marine life would also disappear, following a similar pattern to that of the land surface. This process would begin with the loss of freshwater species and end with the invertebrates, particularly those not dependent on living plants, such as termites, or those found near hydrothermal springs, such as worms of the Riftia genus. Without CO2, photosynthesis can no longer take place. Without plant life to recycle oxygen back into the atmosphere, free oxygen and the ozone layer will disappear from the atmosphere, allowing intense levels of deadly UV light to reach the surface. As a result of these processes, multicellular life forms could become extinct in around 800 million years, and eukaryotes in 1.3 billion years, leaving only prokaryotes. To meet the Sun's energy needs, the nuclear fusion reactions taking place at its core convert around 500 tons of hydrogen into helium every second. The main effect of this alchemy is a progressive reduction in the number of particles of energy the Sun releases. This is why the Sun's luminosity increases with the passage of time. Thanks to an effective greenhouse effect, the Earth has maintained a stable temperature, apart from a few periods of glaciation, which have enabled life to evolve on its surface. For hundreds of millions of years, the Earth has not undergone any significant change in its ocean mass, thanks to the near equilibrium of mantle water inflows and outflows. To maintain water in a liquid state on our planet, it is essential to establish a balance between the solar energy absorbed and that emitted, enabling us to maintain adequate temperatures. This balance is crucial to the survival of life as we know it. When the amount of greenhouse gases in the Earth's atmosphere increases, as is currently the case, a new energy balance is created, where the greenhouse effect creates an additional blanket, causing the surface to warm up. The Earth has an integrated regulating mechanism called the carbonate-silicate cycle, which controls the amount of carbon dioxide in the atmosphere to maintain a stable climate. Unfortunately, this cycle operates on a timescale of the order of 1 million years, making it too slow to be an effective solution for the current global warming problem we humans face. Progressively, even during the current calm period of hydrogen combustion, the Sun is inexorably rising in temperature. Some 4.5 billion years ago, at the very beginning, its luminosity was equivalent to 70% of today's level. By the time of the Great Oxygen Event some 2.4 billion years ago, its brightness had already reached 85% of today's level. For the next billion years, the Sun will continue to produce nuclear energy by converting hydrogen into helium. This is what almost all stars do most of the time. As the Sun converts hydrogen to helium in its core, the average molecular weight increases, leading to a rise in core temperature and the speed of the fusion reaction, known as the proton-proton chain. This gradually leads to an increase in the star's energy release. As a result, the Sun will shine even brighter. When the amount of incoming energy increases, it can also contribute to global warming. This is precisely what happens when the Sun's brightness gradually increases. Although the Earth's climate may experience shorter-term variations due to the seasons, changes in atmospheric composition, such as the addition of man-made greenhouse gases, as well as factors such as volcanic dust and Milankovitch cycles, the Earth's surface is experiencing a slow but steady warming due to increasing solar luminosity. Over a period of time, perhaps even several 100 million years, the Earth's feedback may attenuate this effect. The greater the thermal energy, the more intense the evaporation, hence the increase in cloud cover, which contributes to the reflection of most sunlight back into space. Increased thermal energy means faster weathering of rocks, greater absorption of carbon dioxide, and lower levels of greenhouse gases. Thus, negative feedbacks will preserve life-supporting conditions on Earth long enough. At some point, the Earth's atmosphere will reach a threshold where it will no longer be able to maintain a stable energy balance, leading to an amplification of the greenhouse effect. This phenomenon is often likened to a runaway greenhouse, characterized by positive feedback. As the planet's surface warms up, water evaporation from the atmosphere increases. Water is a powerful greenhouse gas, which reinforces the greenhouse effect and further warms the planet's surface. For several million years, cellular life can persist in such conditions. However, the critical moment will inevitably arrive when the greenhouse effect becomes uncontrollable, warming the Earth's surface to the point where the oceans reach a state of complete evaporation. Despite the increased amount of water vapor near the Earth's surface, there will be no liquid ocean left. After that, it will only take a few 100 million years for the oceans to evaporate, transforming the atmosphere into an endless pool of steam. When ultraviolet light interacts with atmospheric gas, it can cause the gas to heat up further, meaning that more heat is transferred to atmospheric water when it interacts with extreme ultraviolet light. As a result, the water absorbs more energy and heats up faster. This leads to an increase in water evaporation, and consequently, a more rapid loss of water from the Earth's surface. Another way of explaining this is to use the concept of the habitable zone, which refers to the orbital region around a star where a planet can maintain liquid water, provided it has a suitable atmosphere. At present, the inner edge of the Sun's habitable zone is around 95% of the distance between the Earth and the Sun. Our planet will then be completely devoid of life, but the real apocalypse will come later. As the Sun's luminosity increases, the inner edge of the habitable zone will move progressively further out. It's hard to say exactly when the inner edge of the habitable zone will reach the Earth's orbit, but it's estimated to be around 1 billion years. Some extremophiles may still live in refuges at higher latitudes or deep underground, but these will only be ephemeral remnants of a once exuberant biosphere, a situation that could recall the attractive symmetry of life's beginnings on Earth. In all likelihood, Earth will follow the fate of Venus, becoming a hot, barren world. As the habitable zone of our Sun has shifted towards the outer solar system, Mars is now located in this zone. It is possible that Mars's surface temperature will gradually rise. Carbon dioxide and water currently frozen beneath the Martian soil will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially offering a new island for life. According to computer models, the Moon's presence seems to stabilize the Earth's obliquity, helping to avoid dramatic climate changes. This stability is due to the fact that the Moon accelerates the precessional motion of the Earth's rotational axis, preventing resonances between the precession of the rotation and the precession of the planet's orbital plane. The tidal acceleration caused by the Moon slows the Earth's rotation and increases the distance between the Earth and the Moon. As the semi-major axis of the Moon's orbit continues to increase, this stabilizing effect will diminish. At some point, the disturbances will probably lead to chaotic variations in the Earth's obliquity, and the tilt axis could tilt to angles as high as 90 degrees to the plane of the orbit. This is estimated to happen between 1.5 and 4.5 billion years ago. High obliquity would probably lead to dramatic climate changes and could compromise the planet's habitability. When the Earth's axial tilt exceeds 54 degrees, annual insolation at the equator becomes lower than at the poles. It is possible for the planet to maintain an obliquity of 60 degrees to 90 degrees for periods as long as 10 million years. The likely consequence is that ocean evaporation, plate tectonics, and the entire carbon cycle will come to an end. This could happen in around 2 to 3 billion years' time, when the planet's magnetic dynamo could cease to function, leading to the decomposition of the magnetosphere. This would lead to an accelerated loss of volatile elements from the outer atmosphere. In 2.8 billion years, the Earth's surface temperature, even at the poles, averages 147 degrees Celsius, or 297 degrees Fahrenheit. Life is reduced to single-cell colonies in isolated and scattered microenvironments, such as underground caves, and dies out everywhere else. Every second, the Sun emits a solar wind in the direction of our planet, corresponding to a flow of 1 million tons of protons and electrons. These particles are stopped in their tracks by the Van Allen belts, the Earth's magnetic field. Stretching over 70,000 kilometers or 43,000 miles, it originates from the Earth's iron-nickel core. The core is composed of a solid part, the seed, and a liquid layer 2,000 kilometers or 1,240 miles thick. The uninterrupted stirring of the liquid metal layer leads to the formation of the magnetic field. At present, the radius of the inner core is increasing at an average rate of around 0.5 millimeters per year, at the expense of the outer core. Virtually all the energy required to power the dynamo is supplied by the inner core. Within 3 billion years, the inner core is expected to absorb most, if not all, of the outer core, resulting in an almost entirely solidified core, composed mainly of iron and other heavy elements. The remaining liquid envelope will consist mainly of lighter elements that will undergo less mixing. Tectonic plate dynamics are generated by the transfer of heat from the Earth's core to the surface. This heat transfer takes place through the mantle by convection, sometimes combined with thermal conduction. When heat plumes reach the crust, they reach their heat and are pushed out by new hot plumes. This horizontal movement in the upper mantle is the driving force behind the movement of tectonic plates. However, as the Earth cools over time, the liquid outer core gradually solidifies. This solidification reduces convection in the mantle, limiting the power available to move the plates. Eventually, after around 3 billion years, convection will cease completely, putting an end to tectonic plate movements. If plate tectonics cease at some point, the Earth's interior will cool less efficiently, slowing or even halting the growth of the inner core. In both cases, this could lead to the loss of the magnetic dynamo. Without a functional dynamo, the Earth's magnetic field will weaken rapidly over a geologically short period of around 10,000 years. The disappearance of the magnetosphere will lead to increased erosion of light elements, notably hydrogen, from the Earth's atmosphere into space, creating conditions less conducive to life. In around 4 billion years, the increase in temperature at the Earth's surface will trigger an uncontrollable greenhouse effect, creating conditions even more extreme than those on Venus today. This will heat up the atmosphere and raise the surface temperature above 500 degrees Celsius or 932 degrees Fahrenheit, high enough to melt the planet's surface in some places. Nevertheless, much of the atmosphere will be retained until the Sun enters its red giant phase. At that point, the Earth's biosignatures will disappear, to be replaced by signatures caused by non-biological processes. From then on, all traces of Earth's life history will be completely erased. In 4.5 billion years, interactions between the Andromeda Galaxy M31 and the Milky Way will form a new galaxy called Milkomeda. The Andromeda Galaxy, also known as M31, is a spiral galaxy containing up to 1,000 billion stars, compared with 300 to 400 billion for the Milky Way. Made up of gas and dust, it adopts a flattened disk shape and contains a bulge at its center. Originally located 2.55 million light-years away, the Andromeda Galaxy has always been the closest to the Milky Way. It has been gradually closing in on the Milky Way at a speed of 120 kilometers per second, or 75 miles per hour. At first, the two galaxies don't seem to have collided. Being so far apart, the stars will initially pass each other without colliding head-on, before moving apart. Sometime later, this apparent choreography leads to a new rapprochement, this time followed by a strong interaction between the two galaxies. Their orbits are strongly affected by the anarchy of gravitational forces in place during the galaxy's interpenetration. The result, after 2 billion years, is the birth of a gigantic system with little interstellar gas, a new galaxy, Milkomeda. Unlike its two parents, this new galaxy is elliptical in shape, and the stars it contains are scattered around a sphere. The Milky Way and M31 no longer exist. This collision will not disrupt the orbits of planets within the solar system. While the gravity of passing stars can detach planets in interstellar space, the distances between stars are so great that the probability of the Milky Way-Andromeda collision causing disruption to a given star system is negligible. Although the solar system as a whole could be affected by these events, the Sun and planets are unlikely to be disturbed. The new galaxy sees a new outburst of stars, but as the little remaining gas is rapidly consumed, star formation comes to a halt, and the new galaxy will slowly fade away as its new stars die out. In 5 billion years' time, the Sun will leave its main sequence and begin its transformation into a red giant, having exhausted the hydrogen reserves in its core. The energy released during the fusion of hydrogen nuclei in the Sun's core fuels the frenetic agitation of lively particles that exert a powerful outward pressure. It is thanks to this pressure that the Sun swells and does not collapse under its own weight. Until now, this balance has been maintained, but now at 5 billion years, this is no longer the case. Although the Sun still abounds in hydrogen nuclei, there are virtually none left in its core. Hydrogen fusion produces helium, whose nuclei are heavier and denser than those of hydrogen. It is in the core of the Sun that the temperature is highest, at around 15 million degrees Celsius, or 27 million degrees Fahrenheit. The fusion of hydrogen into helium requires 10 million degrees Celsius, or 18 million degrees Fahrenheit. On the other hand, helium fusion requires a temperature of the order of 100 million degrees Celsius, or 180 million degrees Fahrenheit. The Sun is nowhere near this threshold, so as helium replaces hydrogen in the core, the fuel supply for fusion will diminish. Pressure from energy production will decline, and gravity will prevail, causing the Sun to implode. As its gigantic mass collapses in on itself, the Sun's temperature will rise dramatically. Despite this pressure and extreme temperature, helium fusion is still not possible, and the hydrogen then triggers a second phase of fusion within a thin layer around the helium core. As hydrogen fusion proceeds at an inordinate rate, the thrust is much more intense than before. The Sun swells to colossal proportions, reaching over 100 million kilometers, or 62 million miles in diameter, almost 100 times its current diameter. Transforming into a pulsating red giant, it will become thousands of times brighter than it is today. It leaves its main sequence to become a red giant. Naturally, the planets in the solar system will be directly affected by this change. The Sun, with its diminished mass, exerts less gravitational attraction, enabling the planets to migrate to more distant orbits. But do the planets go far enough to win the race against the Sun's increasing diameter? Mercury loses the race, swallowed by the Sun and briefly vaporized. Mars, orbiting further out, escapes unscathed. Venus is lucky. The Sun stops swelling just before it reaches its new orbit, and at the same time, the Earth is also spared. Nevertheless, conditions are fundamentally different. Earth and Mars rotate synchronously with the Sun. The average temperature is now several thousand degrees. What does a sunrise look like from Earth today? Instead of a warm, cheerful yellow disk, a gigantic red circle slowly settles above the horizon. It won't be long before Mars suffers the same fate as Earth. The atmosphere begins to warm. Potential life forms on this planet won't survive another 1 billion years. 2 new orbits are now taking their place in our solar system's habitable zone, the orbits of Jupiter and Saturn. Although neither planet is conducive to life, either Jupiter with water in its clouds or Saturn made up entirely of gas, their respective moons could become suitable places for the appearance of primitive life once their temperatures have risen. In this way, simple organisms could see life on the surface of Saturn's moons, Enceladus or Titan, or Jupiter's moon, Europa. Most of the Earth's atmosphere will gradually be lost to space. The Earth's surface will be transformed into an ocean of lava, with floating continents of metals and metal oxides and icebergs of refractory materials. Surface temperatures will rise dramatically, exceeding 2,000 degrees Celsius or 3,632 degrees Fahrenheit. Then, over 12 billion years old, the Sun's most rapid expansion phase as a red giant will occur in its final stages in 7.4 billion years' time. At this stage, it is likely to expand sufficiently to reach a maximum radius of around 1.2 astronomical units. The Sun will have lost more than a third of its current mass, which will have dispersed in the form of an intense solar wind. This loss of mass will cause the orbits of each planet to expand considerably. Considering only this phenomenon, Venus and Earth could probably escape incineration, but other studies suggest that the two planets would still be absorbed due to tidal interactions with the tenuous gas of the Sun's expanded outer envelope. Forecasts for the end of our planet are therefore rather gloomy. The Earth's gravitational interaction with the Sun's outer atmosphere will cause the Earth's orbit to shrink. The drag effect of the Sun's chromosphere will progressively reduce the Earth's orbit. These effects will partly compensate for the Sun's loss of mass, making it likely that the Sun will eventually engulf the Earth in around 7.59 billion years. The Sun's atmospheric drag can also cause the Moon's orbit to disintegrate. As the Moon's orbit approaches a distance of 18,470 kilometers, or 11,477 miles, it will cross the Earth's Roche limit, meaning that tidal forces exerted by the Earth will break the Moon apart, transforming it into a system of rings. Most of these orbital rings will begin to decay, and the residual debris will impact the Earth. As a result, even if the Sun doesn't directly engulf the Earth, it's possible that the planet will be left without a moon. But the Earth's decaying trajectory towards the Sun may eliminate the Earth's mantle, leaving only its core. Eventually, the Earth's core would also be destroyed 200 years later. According to this gloomy scenario, the Sun's red giant will simply destroy the Earth, which will evaporate into the hot solar atmosphere and cease to exist. But the story of the Sun as a red giant doesn't end there. As the hydrogen nuclei continue to fuse around the core, more helium will flow into the center, and the temperature will rise even higher. The cycle is fueled. Hydrogen fusion in the shell around the core accelerates, and the helium deluge at the center intensifies. This phase will last 500 million years before the core finally reaches the temperature required for helium fusion, a process that produces carbon and oxygen. This transition from hydrogen to helium fusion is marked by a spectacular eruption, during which the Sun contracts to a more constant subgiant structure. This new equilibrium was short-lived. 100 million years later, in the same way that helium had displaced hydrogen, carbon and oxygen nuclei drove helium out of the core and into neighboring layers. The combustion of oxygen and carbon now requires higher temperatures, at least 600 million degrees Celsius. This time, the core will never reach the temperature required to restart nuclear reactions. Its mass is not high enough to reach the temperatures required to fuse carbon and hydrogen nuclei into heavier, more complex elements. The helium shell continues to burn, and the core continues to contract until Pauli's exclusion principle stops the implosion. This quantum mechanism acts as a repulsion. It's as if the electrons refuse to be compressed any further, bringing the sun's contraction to an end. The outer layers continue to expand and cool before being scattered across the cosmos. All that remains is a staggeringly dense ball of carbon and oxygen, known as a white dwarf. It will continue to glow for another few billion years. Fusion reactions will cease, and the temperature is no longer high enough. The sun's thermal energy will be gently dissipated into space, leaving a dark, cold globe. In 9 billion years, the sun, with a mass equal to 54% of its current mass, will become a white dwarf, composed of carbon and oxygen. Our sun is now dead, and its core laid bare. Its power of attraction on orbiting bodies such as planets, comets, and asteroids will have weakened due to its loss of mass in the previous stages. All the orbits of the remaining planets will expand. If the Earth is still around, its orbit is now twice as far away as the orbit we know today. All the planets will become dark, icy, and completely devoid of any form of life. They will continue to orbit their star, their speed reduced by the increased distance from the sun and its reduced gravity. More than 4 billion years later, the white dwarf sun has cooled to a temperature of 2,000 degrees Celsius, or 3,632 degrees Fahrenheit. Its luminosity falls below that of the sun. Its luminosity falls below 3 billionths of its current level. Its heat is no longer measurable. It is now invisible to the human eye. So weak is its radiation that it is drowned in that of the cosmic microwave background. The sun is gradually changing from a white dwarf to a black dwarf. The prospects for the destruction of our planet are not merely speculative, but based on solid predictions based on our scientific advances. Although we have knowledge of the Earth's distant future, it is up to us to shape the short-term future. This perspective raises fundamental questions about the future of life on Earth and our responsibility as a species to be aware of this potential future. It is crucial that we deepen our scientific knowledge, develop environmental preservation strategies, and explore innovative solutions to prepare our planet's biodiversity and sustainability. While this may seem a long way off on a human scale, it remains an inescapable reality in the natural evolution of our solar system. Understanding these phenomena and their implications enables us to better appreciate the importance of preserving our environment and exploring new avenues to ensure a sustainable future for generations to come. This is the ultimate dream of a scientifically literate society, and our only hope of staving off, as far as possible, the imminent threat of human extinction.